Today we are going to study about energy in planetary motion. We have already studied that if there are two masses which are at a distance small r from each other, so if there is a mass and there is another mass, and the distance from the center of one to the center of two is small r, and if this mass is capital M, this is small m, then there is a potential energy in this system, and that potential energy is given by minus G capital M small m upon R. So in a two mass system, the system has energy that is called the potential energy. But now if this object small m is moving, let us say with some velocity v, and this object is at rest, then this system will also have some kinetic energy. Now, so the total kinetic energy of this system will be the kinetic energy of capital M plus kinetic energy of small m. So because we know that capital M is at rest, therefore the kinetic energy of the bigger mass will be 0 plus kinetic energy of the smaller mass will be simply 1 upon 2 mv squared. Now, potential energy is not for independent masses, it is for the entire system. So when we are talking about potential energy, it is the potential energy of the total system. It is not for one mass, because one mass will have zero potential energy. So kinetic energy we have to take separately for each mass, but potential energy will be 1 for the entire system. So if we have to find out the total energy of the system, then the total energy will be kinetic energy plus potential energy. Now in this case we are assuming that the mass small m is moving with some velocity v. Now because in planetary motion the object will move in a circular path, so let us assume that this object, it is moving in a circular path, and therefore at a particular point the velocity will be a tangent at that point. So let us try to draw it again, that if there is a mass capital M and there is another mass and it is moving in a circular path, around the mass capital M, and let's say it's moving counterclockwise, and at this particular point it will have a velocity v. So we are assuming that the planet or a satellite, if it is a planet it is moving around sun, and if it is a satellite it will be moving around any other planet. So we are assuming that it is traveling a circular path. And therefore, if it is a circular path, then we know that there will be some acceleration which will be centripetal acceleration. And if the mass of the object is small m, then there will be a force which will be mac. Also, because it is a two mass system, and we also know that if there are two masses and they are separated by a distance small r, then there will be a gravitational force which will be given by capital G, this mass divided by the distance between them squared, so this will be Fg squared. So at this point we'll also have Fg vector which will also be pointing, this vector, this force will be same for small m also or capital M also, but at the present moment we are talking about the force on small m. So the force on small m will be towards capital M. The capital M is pulling small m towards the center. So this will be the force diagram for this particular situation. So if we have to calculate, we have to write an equation for force from here. It will be all the forces will be equal to the centripetal acceleration into the mass, and therefore we have only one force, which is the gravitational force, and it will be equal to MAC. And we can also write it as mv squared upon r. And the gravitational force we know will be capital G small capital M small m upon r squared. So let us say this is equation number 2 and this is equation number 1. Now let's come back to our energy equation and put the value of kinetic energy and potential energy. So the total kinetic energy of the system will be 1 upon 2 small mv squared, and potential energy. Now potential energy will always be negative, so minus capital G capital M small m upon r. So by using equation 2, because from equation 2 you can find out that mv squared will be equal to G capital M small m upon r. We can just get rid of r, and then mv square will be G capital M small m upon r. So just put this value in this equation, and therefore the total energy of the system will be capital G capital M small m upon r 1 upon 2, because we have this 1 upon 2 factor, minus G capital M small m upon r. So this will give you minus 1 upon 2 capital G capital M small m upon r. This will be the total energy of a system when we are talking about a planetary motion. Now we have assumed for this calculation that the planet or the satellite is moving in a circular path. But if it is an ellipse, if small m is moving in an elliptical path around capital M, then the total energy of the system, and this is A, then the total energy of the system will be minus 1 upon 2 capital G capital M small m upon small a. So this is the total energy of the system, and we have to see that the total energy, it will always be a negative energy, and it means that this much energy is required to bound this system. And if we want to take this mass small m to an infinite distance, then we have to provide this much amount of energy to the system so that we can unbound these two masses. Now we also see that the kinetic energy, so this is the total kinetic energy of the system here. So the total kinetic energy of the system is half of the total potential energy. This is potential energy. So if this is potential energy, kinetic energy will be half of the potential energy. So we can write that kinetic energy is half of the potential energy of the system. Also, we could also write energy conservation equation of this system. Now this entire system is an isolated system. There is no external force. Whatever forces we are having are internal forces. Now this gravitational force is an internal force. So this system, where we are having a planet mass system or a planet satellite system, is actually an isolated system. So if it is moving in a circular path, this system it is an isolated system. So it means that whatever energy it has, it will always have the same energy. So let us say that if at this point it is moving with some velocity v, it has some kinetic energy and some potential energy. Let us say it reaches somewhere here. It is again moving with some velocity, and it will have some kinetic energy and some potential energy. Let us say that the kinetic energy here is initial kinetic energy, initial potential energy, and at this point it has final kinetic energy and final potential energy. Then, because it is an isolated system and there is no external force acting on the system, we can say the total initial energy will be equal to total final energy. So we can write 1 upon 2 small mvi squared plus, not plus but minus, capital G small m capital M divided by Ri will be equal to 1 upon 2 small m Vf squared minus capital G capital M small m upon Rf. So this is a very general equation. We can use this equation in elliptical path also, because it doesn't require a circular motion. We are not using a centripetal acceleration here. So this equation is also valid if the mass or the planet it is moving in an elliptical path. And if small m is here and capital M is here, at this point it has velocity v1, and when it reaches somewhere here it has a velocity of v2, then also it will be valid. And so this will be Ri and this will be Rf. So the kinetic energy initial will be 1 upon 2 m Vi squared, let us say it is Vi and Vf, and potential energy initial will be minus capital G capital M small m upon Ri, and finally kinetic energy final will be 1 upon 2 mvf squared, and potential energy final will be equal to minus capital G capital M small m upon Rf. So we can use energy conservation irrespective of the fact that it is a circular motion or not. So this equation, so for this particular situation, then we can write that 1 upon 2 mvi squared minus capital G capital M upon Ri will be equal to 1 upon 2 mvf squared minus capital G capital M upon Rf. So this will be the total energy of the system in a planetary motion, which is valid for a planet moving around sun or a satellite moving around a planet.